So inference with sample means. So some things we know about working with sample means based on the central limit theorem right now. So central limit theorem says a couple things about means. It says the standard error for a distribution of sample means should be the sample standard error, standard deviation, divided by the square root of the sample size. Oop, why did I put an S in the bottom?
The book always, yeah, I was going to say, the book always gave an N for the sample size.
I think I had half a cup too much coffee this morning.
You drink tea, so probably any coffee is probably too much.
Any coffee is too much for me, yeah. All right, other thing it says is that for confidence intervals, we're going to take the sample mean x bar and add or subtract a magic t-score instead of a z-score, we call that t star, times this standard error right here. And again, confidence intervals are always a sample statistic plus or minus some measure of standard deviations times the standard error is what we have there. And then for hypothesis tests, we have that standardized test statistic, which is a t now. And that's not much different than we've ever done. We're just giving it a different name. It's going to be the sample statistic minus whatever the null hypothesis says, divided by the standard error. And the standard error in this case is that S over the square root of n. So again, these both fit the general pattern we've been working with.
Why did you use the, so the mu is the null hypothesis?
Yeah, when we're talking about means, okay, mu is the population mean, and that always comes from the null hypothesis. So again, the pattern that these two fit down here, this is my sample statistic minus the null value. I'm just abbreviating that with mu, whatever we say mu is equal to, divided by the standard error. So in each situation, we get to say, okay, what's the sample statistic here? What's the null value here? And how do I get the standard error? And last week, we were just given a number. This week, we are going to calculate them. And then the confidence interval, the pattern there is always sample statistic minus some z or t score, we were calling it a z-score before, times whatever the standard error is. So the context is different. Instead of a proportion, we get to use stuff related to means. All right, so let's look at an example. So the example I'm going to pull the first one from StatKey and just go to hypothesis test. Yeah, let's go by hypothesis test for a single proportion. And I'm going to use, no, proportion mean, carry what the heck. And I am recording right now, right? Yeah, good. Single mean, there we go, that's the right button. And I'm just going to use their body temperature data. And here they say their sample size is 50, their mean is 98.26, and the sample standard deviation is 0.765. So I'm going to write this down. Sample body temp from StatKey. According to the StatKey summaries N, there were 50 in the sample. The sample mean was 98.26, and the sample standard deviation was 0.765. Do I have enough information here to calculate the standard error? The answer is yeah. To calculate the standard error for a sampling distribution of means, I just take S and divide by the square root of n. So that would be 0.765 divided by the square root of 50. 50. I'll plug that in the calculator. Let's go here. So 0.765 over 50 in the square root. I can type that right. 0.1 to 4 decimal places, 0.1082. Would be the approximate standard error there. If I wanted to make a confidence interval on this right here, I need to know a little bit more information. I would need to know a confidence level, and I need to know the sample data. So typical confidence level is 95%. So let's say we want a 95% confidence interval. Then again, our formula for a confidence interval is always the sample statistic plus or minus some z or t score times whatever the standard error is. For a confidence interval, that z or t score is based on a 95% middle here, so we'll have to go out and find that. So right now, what do I know? I know the sample mean, the sample statistic is 98.26 plus or minus, I gotta find that z or t score, and then I just found the standard error there. That's about 0.1082. So to find a z or a t score, I either need to use the stat key, normal, or t, or a spreadsheet. So I'll do both of those. Let's go over to stat key and home. So this is the central limit theorem, which is a theoretical approach to these. And I'm going to do both the normal and the t to compare and explain what's going on here. So normal, that one screen, t in the other. So I'm at the stat key homepage. First thing I'm going to do is go to normal. And to get a z-score, we've done this plenty of times now, I get the normal, and then I just say I want two tails, and I just tell what percent goes in the middle. In this case, 95. So if it was a z-score, I would say it should be 1.96. Why do I use a t-score instead? So the reason we're going to use a t-score is the following. I'm trying to estimate a population mean here with a confidence interval, right? That's the point here. So in order to estimate it, I can't say my sample of 50 people is exactly the population of humans on the planet. That ain't true, right? There's way more than 50 people. There's a lot of diversity here. So I got to come up with a margin of error. To come up with a margin of error, I got to figure out, well, what should the spread be? Well, there's a certain spread in how wide people vary in their body temperature in the world. That would be the standard deviation of the population. So I get this problem here. But what is the standard deviation of the population? I don't know, right? How can I know that if I don't know the mean? And that's called sigma. I don't know sigma. I don't know mu. So to deal with these two levels of uncertainty, people realize that the distribution of the sampling distribution is going to have to be a little bit wider than we think because we have two levels of uncertainty. So what the t distribution takes into account is not only what we think the middle might be, but what the spread might be and the sample size. It takes all three of those factors into consideration. And it does that basically by looking at what is the spread of this z-score for the given situation. In order to do that, since we've taken into account here the center in what our data says, or what we think the center might be, to take into consideration that unknown spread on the bottom, we just need to give it a little extra information. and that is what's the sample size. So notice normal distribution didn't care what the sample size was. That is not in the calculation here. If we switch to a t distribution, first thing the t distribution says, what are your degrees of freedom? And the degrees of freedom are always 1 minus the sample size. So if I have a sample size of 50, degrees of freedom is 49. And I'll write this down in the notes. Two-tailed test, 95 in the middle. So notice now I'm looking out a little farther on each side. Instead of 1.96 to the right and left, the t-distribution says, nah, we get more uncertainty. We got to look a little farther out to find what we're looking for. So now it says make the spread 2.01. So for a t-dist, this idea of taking the sample size minus 1, that's called degrees of freedom. So now we know that if we're asked for what are the degrees of freedom, that means just take the sample size minus 1. And according to StatKey, that should be, in this case, for 95% confidence level, 2.01. And the extra 0 really doesn't help me here. And that will give me my confidence interval. So let's go to a spreadsheet and build that. So here, and this was depression, hypothesis test, and this is the same spreadsheet I was at earlier. If you're new to our conversation here in Zoom, I'll reshare the link. If you're on YouTube, check out the description underneath the video. And we need a new tab. We're going to do confidence interval for mean. And either we need the data or the summary statistics. So there's going to be two different versions of these spreadsheets. So here I have the summary statistics. So I'm given the count, that's my n, that's 50. And to use the number, the n equals and the 50 have to be in different cells. I can't type n equals 50 in the same cell and use the number 50. And then I need to know the sample mean, that's x bar. And we're given that 98.26. Otherwise, I have to get the data and calculate it. We'll do that next. And then I need to know S, the sample standard deviation. Again, we were given that 765. Oops, mistype 765. And then I also need the confidence level. So these things need to be given in order to figure out the confidence interval. 0.95 space. The next thing I usually want to figure out is what's the relevant Z or T score based on the confidence level, and I need to know what the standard error is. So I'm going to do the standard error first. So standard error based on the information above, that's always the sample standard deviation divided by the SQRT of the sample size, or mean. And there's that 1.082 that we had earlier. To get the relevant t-score for the spread, I usually find alpha, the tail, what the tail probabilities have to share. And then I cut that in half for each tail to find the z or t score. So then, yes, I do need that alpha 2. Okay, so alpha is always 1 minus confidence level. And we're building a spreadsheet that can be reused, which is the nice thing. And then here, I want to cut that number in half. So equals this divided by 2. So that tells me what the tail probability is. And I need that to find the right t-score. So now I can find my t-score. Calls it t or z star. And that's going to be equal to, I want the t dot dist, and there's a bunch of different versions of them. There's the t inverse, t dist right. What are we going to use? I think we're going to use the t dist. Wait, no, given a probability, I want to find the t-score. That's t inverse. Okay, we want t inverse. T inverse says, what is your tail probability? So that's that alpha over 2, comma, what are your degrees of freedom? And that would be just my n, but minus 1. Let's see if I did that right. Yeah, and like before, it's giving me the left tail number. If I were to round that to 3 decimal places, that's going to give me that 2.010 that stack key claimed. And I'm just going to sneak in front of this and get rid of the negative by making it a double negative, like I did the other day. So that's my t-score. So looking back at my notes, to find a confidence interval, I need the sample statistic, got it. I need the t-score, got it. And I need the standard error, got it. Okay, so we're ready to get the whole interval. And so then maybe go down here, I can find my lower value, I can find my upper value, and then maybe we'll find the margin of error also. So lower, that's always the test statistic, x bar in this case. Lower is a minus whatever your count of standard deviations is, that's the t in this case, times the standard error. And always double check you click in the right places. And this is not an autofill. Repeat, but with a plus. Sample statistic plus about 2 standard deviations from the mean using the standard error. And that plus or minus thing we did, that's just the margin of error, right? We add and subtract the margin of error, which is just the t-score, in this case, times the standard error. So what can I say here? I can say that based on this sample, I expect average human body temperature to be somewhere between 98.04 and 98.48 degrees Fahrenheit, or I can say it's about 98.26 with a spread of about 2.217 degrees Fahrenheit. So there's 2 ways I can talk about that here. Is 98.6 in my interval? The answer is no, it's not. So we could run a hypothesis test next to think about that. And just add this to my notes. So we think, based on doing the plus and the minus here, that our confidence interval, our 95% confidence interval, is parentheses, the lower 98 point, I'm going to go to 2 decimal places, 0.4, and it could be as high as 98.48 degrees Fahrenheit. Is what I think it is. So I'm 95% confident that average human body temperature is somewhere between 98.04 degrees Fahrenheit and 98.48 degrees Fahrenheit. So again, normal distribution versus a t distribution. Since I'm doing a mean and I don't know the mean, or I'm questioning it, and I don't know the spread, we have to look to a t distribution to deal with those multiple levels of uncertainty, which just makes basically the interval a bit wider to deal with the multiple layers of uncertainty. If we had just run a normal distribution, the interval would be slightly narrower, and it's more likely we'll miss out on what the actual true mean is for the population. Next, let's talk about a hypothesis test for mean.